Okay, cool. So let's start with picking up where I got things very wrong in the last session. Again, I'd like to apologize for that. That will teach me to try to add something on the morning of the lecture. Uh, so the what I meant to say is if you run your simulation or a short part of your simulation, just to get an idea of how this works, with the neighbor modify command with delay 0 every 1, check yes. What this will do is, as we discussed before, delay 0 means you never delay between builds. Every 1 means you try to build a neighbor list every single time step. And as we discussed in the previous session, the check yes means that if none of the atoms within your neighbor list have moved more than half of the skin distance, i.e. if none of the atoms have made it from the very edge to the midway point, uh, then don't bother building a list. And that's what the check yes does. And if you run with these commands and look at your outputs, you will notice that depending on like the density of your system, depending on the number of atoms in your system, the temperature, that sort of thing, your neighbor list builds should change and should vary. You can take the number output in the neighbor list builds, which when I ran it with these commands just now, I got that in 10,000 time steps, the neighbor list had to be built 500 odd times. And from that, you can kind of work out the frequency at which you need to build neighbor lists. And the way you do that is you take the total number of time steps, as I said, 10,000, you divide it by the total number of neighbor list rebuilds, in this case, about 500, and you get that, well, you could technically use a neighbor list rebuild frequency of about 20, maybe a bit more than 20, but let's call it 20, and you'd be fine. And that's it. That's how you can use that information to then set your neighbor modify. So in this case, I would set it to delay 0 every 20 and then check no, because I've done that short test with the check yes in order to out how frequently I need to rebuild the neighbor list. Provided that your system doesn't change too much in properties, then that should be fine. So provided that you're looking at a stable or near enough stable system. And the other thing I feel I glossed over is that we've mainly been looking at changing the neighbor list frequency to decrease the neighbor list times. There's two other things that you can change that will improve the speed of your neighbor lists. The first one is you can decrease the neighbor list cutoff, i.e. decrease that gap between the end of the short range interactions and the start of the neighbor list, the end of the neighbor list. And that'll just mean that there's less atoms that are within that boundary. And then you'll be doing, and that can mean that you do less calculations. Like if your neighbor list cutoff is enormous, then you end up having way more atoms than you need stored. So decreasing that can be a good idea. And the other one you can decrease is your short range interaction cutoff. If your short range interactions are really quite long, or have a very large cutoff, you can definitely reduce them and still get most of the same results. And that'll also mean that because the neighbor list cutoff is your short range interactions plus a delta that you define, that decreases the sphere of volume that you of information that you save for every particle. So those two things I wanted to quickly mention. The other one I wanted to mention is there was a question before the break, which was to do with using the multi command. This is the neighbor style multi. And let me see if I can find the question. Actually, I logged out and back in, so I won't be able to find the question. But roughly speaking, if I remember, the question about multi is it only ever useful for is it only ever useful if you're looking at a surface with gaps in it? And the answer is no, definitely not. I've actually used the multi command. I was looking at a simulating polydispersed frictional particles. And because some of my particle volumes were 4 times the volumes of another one. Oh, thank you very much, Stephen. The question was, what if you use neighbor style multi? If you had a lot of small particles, is it bad practice? Should it only be used if you have a gap graded material? So no, again, like the answer is no. You can use it in multiple occasions. If you've got particle sizes that vary wildly, it can really improve the speed of your simulations. Namely, what you do then is you kind of consider you're able to set different cutoff distances for the different sized particles, which means that your small particles will have like nearby neighbors and your large particles will have further away neighbors, which makes sense. Large particles are likely to have more smaller particle neighbors, so other large particle neighbors, but small particles won't really care that much about the big particles, or they'll sort of look like walls to them if the discrepancy in size is large enough, right? Cool. Great, so that is everything I got wrong last time, now hopefully fixed. Let's move on to the next section, which is, this one should be a quick introduction to the LAMMPS rerun command. The LAMMPS rerun command is one of those fantastic ones. So we've really tried up until now, and I think this is the last one of this set of sessions. What I've really tried to do is to think of useful tips that can make your simulation run faster and more efficiently. This is one of the run more efficiently ones. Of essentially, it's a trick whereby if you run a simulation that produces a LAMMPS trajectory, and then you realize, oh, I forgot to run something, you can use that LAMMPS trajectory and use the snapshots within it to run a fake simulation within LAMMPS to recreate some of the information that are used. Sorry, I realized I wasn't sharing the right thing. There we go, that looks like what I wanted to do. But yeah, so you can take the LAMMPS trajectory that you've generated and run that through LAMMPS to calculate some of the properties that maybe you forgot to calculate, or maybe you want to calculate afterwards because, well, actually the calculation for it is a very serial process and you don't want to waste the time of hundreds, thousands, tens of thousands of cores while you wait for this one tiny bit of serial code that you can do in post-analysis to run. So it can be used for a number of reasons. It can be reruns can be used to calculate thermodynamic properties, compute system properties like the radial distribution function, the mean squared displacement, using some computes, LAMMPS computes once the simulation is finished. You can simulate a system. Like once you've got your snapshots, you can kind of go, well, okay, this is great, but what happens if, I don't know, for instance, I've been running my Leonard-Jones system with a cutoff of 5 sigma. So I sort of like, if my particle radius is sigma, then I sort of cut it off at 5 times that. Does it make a difference if I drop that down to 3 point? You can do that test by changing the potential before you then load up all the images and see what the energies and pressures and all of the thermodynamic properties would be like. And then finally, you can compute properties of a system that would have been costly to compute during the initial run, which I think I've already mentioned. So as I described before, if you've not done so yet, this next exercise is exercise 2 in our set of exercises. If you've not downloaded it yet, you can download it with the svn checkout command, and then you can just go into exercises and 2/post analysis, and you'll find that there are 3 files in there. There's an in.lj start, which is a LAMMPS input trajectory that will run a simulation of a small Leonard-Jones gas and generate a LAMMPS trajectory file from it. The I think it should be LJ rerun rather than rerun. It's a LAMMPS input script for performing a LAMMPS rerun from the trajectory that you've run before. And then just the sub.slurm file lets you run in.lj start on the compute nodes. So if you, let me switch back to my terminal. Let me clear that because that's quite, yep. There we go. So if you go into the place where you've got exercises, you go exercises to post analysis, you've got in LJ rerun, in LJ start, and sub.slurm. If you look at sub.slurm, you'll notice that all it does is it runs on 128 MPI ranks, 1 OpenMP thread per rank. It runs the file in.lj start. If you just run sbatch sub.slurm, this Leonard Jones system is much like it's a much smaller system than before. So it's running. It has no long-range interactions, so there's no case-based calculation. So it'll run much faster just because of that. Long-range interactions are costly. Yep, and it's just running a 40 by 40 by 40 box for about 100,000 time steps. Apparently, it's running it for about 200,000 time steps. 100,000 to equilibrate and 100,000 to output the LAMMPS trajectory file. Still running. If I remember correctly, the thing that I'm outputting in this is the only thing that's being output in this, apart from the LAMMPS trajectory file or dump file, the names are used interchangeably. Only things I'm outputting are the time step and how long it took to get to that time step. So runtime up to that step. That's not username. Yeah, that won't be happy. Oh, and that's nearly done. From memory, it takes about 1 or 2 minutes to run. And please feel free to do the same sbatch command as I've just done. I forgot to mention, if you've clicked off, it's nearly done. And yeah, if you're running this in background, there we go, it's done. So 3 minutes apparently. So once that's done, that script has generated a couple of things. It's generated a LAMMPS log.out file, and that's going to be super boring because all it'll have is time step and how long did it take to get to that time step in seconds, which is not the most exciting. Also, I'm outputting way too often, and then there's your timing information. And then you'll notice if you do another run command, your CPU time goes back to 0, which I find interesting. And then right at the bottom, you'll notice that, well, we've got pair, we've got neighbors, we've got comms. So comms is really high, which suggests that I'm running on too many cores, which is probably entirely correct. I just used a whole node for this because, I don't know. One of the terrible things about working on really large systems is you end up thinking, well, a node must be the most basic block, but it really isn't. And I could be more smart about how I use these resources, but there you go. And there's no case base. The other things it generated are a NVT LAMMPS trajectory. That's the LAMMPS trajectory we'll be using in the rerun. And then all of our jobs have created a slurm minus number.out. That's just a slurm, the scheduler we're using on Archer 2, produces this file as an output for like to put any outputs that would go to screen, they instead go to this file. Okay. So now let's take a quick look at our in.lj rerun file. You'll notice that in the in.lj rerun file, there's a bit more things of interest. So first of all, I've not really changed the potential. Most of it is the same until you get to around here. Bits that changed are, I'm now running, I'm now looking for more thermodynamic outputs. So I'm looking also for temperature, the total energy, potential energy, kinetic energy, pressure, volume, and density. I also want to calculate radial distribution function. Okay. And that radial distribution function, I want it to be the average of like every 100 time steps, take a snapshot and do that for 1,000 times, so that you're doing it for 100,000 time steps, and use all of those averages to average out your final radial distribution function. This is a super small what's the word I'm looking for? Script. So it should run really quickly, even on a single core. So I'm going to be using a single core. first thing to do is make sure that all your modules and your, oh, that should be Nate. Not that it matters. Make sure that all of your modules and your paths are set to what they should be. You can do that by copying, I'll actually paste this in the Etherpad. Where is the Etherpad? You use all of that. And then we will be running on one of the Archer 2 serial nodes. And Archer 2 has a number of serial nodes, and what these nodes do are, if you are going to run a small job that's going to be really quick, like the one we're about to run, you can use one of these nodes to ask for just a single core. For most of the Archer 2 compute nodes, you need to ask them in integer numbers. And it's actually one of the annoying things, like as I mentioned briefly, my what was I going to say? My script right there clearly indicated that I was using too many cores to run it. There was a lot of time spent in communications. Archer 2, I lower the number of cores that I use, but I'm still asking and paying for an entire node. So yeah, the serial nodes are a way to get around this. So I'm going to run on a single processor, minus N1, giving it a maximum time of 5 minutes, and then on the serial queue with my account number, and hopefully this will run. Hopefully. The other one you can do, maybe a bit less recommended, is because this is quite a small job, you can just run this part, the login nodes, and that should be okay. But it's probably better to run on the serial node. What does the in.lj rerun do? That's an excellent question. I didn't mention it, which is really bad. Oh, it was running in the background. That's cool. The in.lj, so what does it do? It a lot of this up to time step is exactly the same as up to the time step in the .start start file. So up to the time step, it's exactly the same. Past the time step, I've added a couple of things. The things I've added are a different thermostyle, a new compute. Then instead of having a run command, I use a rerun command where I define the LAMMPS trajectory that I'm using. I tell LAMMPS that it's a dump file, and then I tell it it's got the first number you'll see per atom is the X position, the second is the Y position, third is the Z position, fourth is the velocity in the X direction, velocity in Y, velocity in Z. And what LAMMPS will do is it will read your file step by step, look at the position of all the atoms at that one step, and calculate all of the properties that you've asked from it. So it'll calculate all of the thermostyle, it'll calculate all of the RDFs, all that. Hopefully that makes sense. Oh yeah. Cool. So that's that question. The next question, I'm getting an error. It seems like, does it do some sort of post-processing? It entirely does post-processing, yeah. So where was I? Yes, I wanted the Etherpad, and I wanted just copy. Just for the sake of brevity and to show you what the output looks like, I will run this on the login node. Do not run this on the login node. You'll see basically it's running. Looks like a LAMMPS simulation, but it's entirely just taking snapshot by snapshot the snapshots that were output to the LAMMPS trajectory. How many time steps is the rerun? It's 100,000. How did reruns deal with periodic boundary conditions? My understanding is you define the periodic boundary conditions. So at the very top of my LAMMPS rerun command, if I go up, hopefully it'll still have come out to log. Where is it? No, it has not. But it is like you can use a LAMMPS rerun command to take a non-periodically bounded box and simulate it as if it was under periodic boundary conditions. Like you can redefine it, but you get to define what the periodic boundary conditions are, whether they exist and how you deal with them. I'm thinking that maybe this is a bit of a bigger system than I meant to run. Cool. Could you try? This shouldn't make a difference. So I'm sorry, the export commands once again, but cool. Could you try running module restore, then running the commands that are on the Etherpad, please? And so this is running quite happily. Kind of see what it does. I would recommend actually decreasing the region size to, I don't know, let's do 10. Doesn't really matter. That'll run way faster. And then having a go at the exercise for this bit of the course. Let me get the exercise up. And the exercise really is, well, what happens? So there's two exercises, and please feel free to choose which one you're more interested in and do that one. The first exercise is to try to get you to understand a bit more about the limitations of the LAMMPS rerun. And it's sort of saying, well, if you look at your in.lj rerun file, the RDF is being calculated every 100 time steps. What happens if you calculate it every 500 time steps instead? And what about if you do it every 50 time steps? And the second exercise is sort of talking about the other thing we were talking about, of you can change your pair styles and see what the simulation looks like. So at the moment, we've got a pair style set with a cutoff of 3.5. What happens if you drop that to 2.5 or 1.5? How do the total energy change as you do that? So if you want to do those for the next 3 or 4 minutes, and I will see if there are any questions that I can answer in the chat. So one of the questions is, can the post-processing also be done in parallel? Yes, yeah, it totally can. Here we go. I will try to show this. One of the fun quirks of Chapter 2 is that the serial nodes let you run parallel jobs up to 32 cores. So they're interestingly serial. Okay. So did the module restore reloaded everything and still giving me an error? Are you running in your in a TA058 account, or are you running in your own project? Okay. That's weird. It really shouldn't be giving you an error. It looks like, do you have a module load lamps command in there somewhere? Like in the Slurm submission script? Do I have a module load command? That's the wrong one. But that looks like the error you're getting indicates that you're trying to run the central install of lamps rather than the one for this course. So I would suggest you log out and back in, and that should clear your path, though it should have been cleared anyways. Yeah, that'll be the issue actually, because the LAMMPS module uses the Cray programming environment 2109, whereas we're using 2104 for the course. So if you log out and back into Archer 2, it'll clear your path, and then you should be able to do the copy paste and it'll work. Is the rerun command generating an entire new but shorter empty trajectory, or is it just calculating RDS from the LAMMPS trajectory dumped from the longer simulation? It is doing the latter. It is the rerun command only looks at what is in the LAMMPS trajectory. And actually, that answers the first of our two questions. But the way that the rerun command works is it will open your LAMMPS trajectory file and take the first frame of that trajectory and use that as if it was the simulation position right now and do all the calculations you want it to. It'll then move to the next frame in the trajectory file and do the same. And it keeps repeating until it's gone through all of the frames in your LAMMPS trajectory file. Which does have one huge limitation, which is that if you were interested in any details that happen between any of the frames in your LAMMPS trajectory file, and note that in this case we're running a system where the LAMMPS trajectory file is output every about 100 time steps, then you're not able to have that information because it doesn't exist. It's not in the LAMMPS trajectory file, so LAMMPS can't do anything with it. Cool. And for the second question, because I'm aware of time, for the second question, what happens if you change the potential? What should happen if you change the potential is there's for a Lennard-Jones potential, I would expect that there's not very much change in the total energy when you change the truncation distance from 3.5 sigma to 2.5. The energy will be ever so slightly lower, 2.5 than 3.5. But if you change it to 1.5, then there will be a drastic noticeable change in your energy, and that's because of the way that the Lennard-Jones potential is. Sort of dies off relatively quickly, but it doesn't really die off properly until you've reached about 2 to 2.5 sigma. So that sort of also, that was more there as an exercise to give you an example of, well, look, you can actually change potentials and use totally different potentials as part of the rerun command. But yeah. So just in conclusion, the LAMMPS rerun command is very powerful and can have many uses. You can really get a lot out of it. But it is limited to the information that's fed into it, which is in turn limited to the information contained in your LAMMPS trajectory file. So you can use it to extract information from an existing simulation trajectory, but it's definitely not a new simulation. You can't generate, you're never doing time integration, that sort of thing with it. Cool. So hopefully you all found that interesting. And now we will move on to the next section, which will be presented by my colleague Stephen, who will be talking about Replica Exchange.
Hi, everyone. You should better hear me, although I think you actually can't see me because my camera has failed me, but that's okay. MacBooks are a bit annoying for that. Yeah, so
I definitely see you, and I can't.
Okay.
Wait.
Can you hear me or not?
I can hear you. I cannot see you.
Yeah, okay, yeah, you're not going to be able to see me because my MacBook has decided to block me sharing my camera, and it's quite annoying to redo it, but I can share what I'm going to show you. Cool. All right, yeah, so this bit is so it's a bit less general than the stuff we've covered before. So the bits Julien covered were it essentially applies to anything you might be doing in LAMMPS, and sort of you can use the things you've learned there, and in general they're good things to follow. In this bit, we're sort of doing a more specific example of one of the more sort of complex or advanced things you can do with LAMMPS. So for people who've done quite a lot of simulation, you'll know that there's various enhanced sampling techniques that you can use. So like one way to speed up your simulation getting results is you can run it for longer, or you can run it with more cores. But then another way is you can do your simulations in a sort of a more clever way. So you can get more out of your compute time by doing things in a enhanced ways. So one of those methods is Replica Exchange. So this is one that we've chosen this, I guess, because this, although it's a specific method, it's quite a general method, and you can apply Replica Exchange to most systems, and the way you do it is the same for most systems. So you might well have seen a picture like this before. If you've done probably more biomolecular simulations, you would have seen something like this. So you have the black line is a potential energy surface. So whenever we're simulating something, we have its potential energy. That's how we describe it. And then LAMMPS uses this potential energy function it uses the forces, and then it uses the integration method to sort of move our system through time, and it will sit in this potential energy surface. Now, depending on what the temperature is of the system, it can more easily access different parts of the potential energy surface. So if you're at a low temperature, which would be below this blue line, and you're stuck in one of these sort of minima of the potential energy surface, if you're at that low temperature and you start your system in one of these, it's probably just going to stay in that specific part for a long time. So the usual example of this would be if you're looking at protein folding. If you start a protein in its one of its dense states, a folded state in one of these, and you start your LAMMPS simulation, it's just going to sit in this folded state for a very, very long time. And you can simulate it for days or years, and it's probably not going to change. But we know that proteins have lots of different states, and in fact, the folded state you have is probably not the global minimum folded state, which might be this one. So if we want to then see what this state is using molecular dynamics, one way we can do that is by using this method of Replica Exchange, where we use the fact that if we had a high temperature system, it will be up here where it can very easily access these different states. So the idea is if you start a system in one temperature and one state, you can run copies that work their way up this temperature scale. So then the higher ones can explore, and then when you move down the temperature scale, it's going to end up in a different one of these states. So it uses parallel programming in a slightly different way, whereas instead of just splitting up our simulation and using this domain decomposition to make it run faster, we actually run multiple copies of the system in parallel at different temperatures. And the hope is that although you're going to have to run lots more copies of your system, the fact that you can do this enhanced sampling means that you are going to sample more interesting states, is the idea. So if you've done any Monte Carlo, which is sort of another method, it's a different method to molecular dynamics that you've probably come across. You would have seen an equation similar to this, but this is just one of the important bits of maths that you sort of want to bear in mind when doing Replica Exchange. So if you have two systems, your two replicas at different temperatures, you can swap the coordinates, or in fact the temperatures between these two replicas, based on this metropolis exchange criteria. So the only information it needs is the temperature of both replicas, so T1 and T2, and their current potential energy, which is these two energies. So you have your two replicas, and then you know the temperature because that's the number you set in LAMMPS, and then you know the energy because that's what LAMMPS is computing. And then you can compute the probability that you can exchange them. So you work out this probability, and then obviously if it's 1, that means you're always going to accept it, but it's not going to be 1, it's going to be less than 1. So then you have a number that would be a number between 0 and 1, and then you can then generate a random number that is also between 0 and 1, and then you see if that is lower than this, and then you'll accept the change. So that's how Monte Carlo is done in general, and that's how it's done in this example for Replica Exchange. So an example system we're going to use is it's a polymer. So it's a polymer of 50 beads. This is quite a zoomed out picture, but you can see there's 50 beads, and this is similar to the previous ones. It's a Lennard-Jones system. So you can get the examples from the same place as we had before. So we had this exercises folder. We're now in number 4. Actually, we're now in number 3. I think the numbers changed since I wrote this. So I'm now going to switch my screen to my terminal. All right, so this screen, we got to terminal. Yes, okay. Yeah, so it's this one, number 3, Replica Exchange. So just the numbering slightly different to I had it online. So can everyone see, is my font big enough for everyone to see?
It looks.
Yep. So in this folder, we have several files now. So as before, we have a submission script, and we have an input script, and we have our data file. So the data file is the image I showed, and the image you can see on the course material. So that's our polymer in that initial configuration, where it's like in a very unphysical extended state. So now if we're going to look at our run script, and we're going to see how it's different to a normal LAMMPS run script. So the first part is that if you want to run these replica simulations where you have multiple copies, LAMMPS has this new variable type called world, which we won't have seen before. So world means that it's a specific one that LAMMPS knows what to do with if you're running multiple simulations. So it means that the number of variables you have to equal the number of LAMMPS simulations that you're running in parallel with each other. So there's going to be a keyword partition that we use soon. But if you have 10 partitions, you need 10 variables. So here we have 10. So this means we're setting the temperature of each of our replicas, and then we're giving them this ID, which is also 0 to 9. So these variables will then be used in the script to distinguish them. So the first place we see they are is this in our thermostat command. So this is what's setting the temperature. So we see this is just the start temperature and the end temperature, but they're both the same because we want constant temperature simulation. So the question, can the values of the variables come from a text file? I imagine you could do that, yes. I don't know the exact syntax to do that. But yes, I imagine you can do that. So here we have the temperature where we are setting the temperature of each simulation. So simulation ID 0 is going to start off at temperature 300. Then simulation ID 1 will be this temperature, and then up to number 9, which will be running at 1000 Kelvin. So the moment I'm using real units just to make the temperatures make sense, essentially. So that's our temperature range. We're going to run from temperature 300 up to temperature 1000. So the next part we have is this, we use the I variable, so that's our index. So that means that simulation 1 is gonna, or in fact simulation 0, will be saving to this trajectory file. So they each print to their own trajectory. And then the final command is, so usually here, this is where you put your run command. So this is saying you've run for 1,000,000 time steps, but in fact it's using this temper command, which is how it does the parallel tempering. So it says run parallel tempering for 1,000,000 time steps, and then every 100 steps it's going to try and switch the temperatures between replicas, and then you have to give it the initial temperature that it's starting off with. Then you have to tell it which of your LAMMPS commands is a thermostat. So this number 2 corresponds to this one, just so it links up that it's changing this command when it switches replicas, and there's just 2 random number seeds. To run this, you just need another slightly different command, which we'll see in the Slurm file. So as before, everything should be similar to what Julien said, but apart from here, we have the run command. Then we have this additional flag, which is the partition. So this tells LAMMPS to run. This tells LAMMPS to run 10 copies of the same simulation. And specifically, it's telling it to run 10 copies, each using 1 processor. Because this is a small simulation, we can do this. If you wanted to run it in parallel, you could go 10 copies and change this to 2. Then make sure you change the total number of tasks from 10 to 20. But if you do that for this small example, you're not going to see any difference. So let me just check. There was a question. How do we tell it which temperature to change to? So the temperature scale is the one we have listed at the top of our run script. The idea is you don't tell it, you only tell it which temperatures you wish to run with. You can never tell it specifically what to change to. So it decides using this sort of random number probability distribution which one it changes to. So the reason it has to do that is it has to satisfy detail balance for the Monte Carlo step. That's how you end up sampling sort of the correct canonical distribution function. So another big question, so I guess first we can just run this to make sure it runs, and then you should all be able to do this as well, and it should just work. If you do sbatch run, this will submit. You can see it's running. It should take, I think it's about 15 seconds it takes to run, or definitely less than a minute it should take. Maybe not. You'll see. So with these simulations, you're going to see a lot of stuff printed out. So before we just would have one log file and one of these Slurm files. Now we have the Slurm file, we have a normal log file, sort of an overall log file. Then we have a log file for each of the 10 replicas. We have a trajectory for each of the 10 replicas. And you also have these ones called screen.0. So this is this text that would normally be output to your screen, which if you're running interactively, that's the stuff that gets printed to your terminal. If you're running a normal LAMMPS job, it's the stuff that gets printed out to this file. But you end up with these screen files that list the normal stuff you would get for each LAMMPS simulation. So we see that for replica 0, it's run for 16 seconds, it's run 1,000,000 time steps. Okay, this is something that I haven't checked until just now. This is something we may have covered earlier, but if you see a dangerous build equals a number that's not 0, that means you need to check your neighbor list settings, which is something we would have mentioned. All right, yeah, so here where I specified the neighbor list, I did not specify, so the stuff we learned before that Julien told us, you you can select how often it checks a neighbor list and how often it builds it. So as I haven't done that, it uses the default values, which I believe are delay is 10. So what we've learned here is that with delay 10, it's delaying. We need to reduce that. So you want to run this with delay 1, check yes, and every 1. Then I imagine our dangerous builds would disappear. But I think as we're running on one process, we don't have to worry as much about these dangerous builds because it's not actually communicating stuff. So you run multiple simulations without using a loop command. Yes, so if in LAMMPS, you can run multiple simulations from one script using a loop command, and then it will run these simulations one after the other. We are running them at the same time in parallel. So yeah, it's different to a loop command. So let me just check. So now we have now run the simulations. So hopefully everyone's. Yeah. So Julien said so the default is delay is 10. So for this case, we can actually change that now. Everyone check yes. If I spell everything correctly, which I probably haven't, we can run this again. And it's running. So we just overwrite all of the files, which is fine. Let's wait for it to finish. All right, yeah. So now we see there's no dangerous builds, and so actually that was a good example of using stuff we've learned before as to how you can check your neighbor list. So we actually found that the default settings were too high, which is not good. So now we're back to dangerous builds is 0, which is fine. So if you wanted to, we could use this number and then slightly increase the delay, but it doesn't matter too much. So we're just going to briefly go to how you can choose a temperature scale to use for your simulations. So it's not the easiest thing to do, choosing the temperatures. So you want to have them such that you get a reasonable chance of having this acceptance ratio between the replicas. If you've done any Monte Carlo sampling at all, what was the command you used to eliminate the dangerous builds? Yeah, we can just go, it was just changing in the script. There was this neighbor modify command that we had before where we were changing it, but the default is delay 10. So I explicitly put it in and changed delay to 1. Yeah, so if you don't any Monte Carlo sampling before, you'll know that you want a number that's about 30% chance of accepting these Monte Carlo moves. The reason it's 30% is I cannot remember, but there are some papers that sort of derive it. So I use this, there's this temperature calculator essentially, which you can use, which I used, where you can put in, if you want 0.3 probability, and we want to go from 300 Kelvin to 1000. And then we have 0 water because we have a coarse grain polymer, but this is more for all atom biomolecular simulations, but it still works pretty well for any sort of simulation. And we put 50 protein atoms. It tells us if we want to span our temperature range from 300 to 1000 and we want this probability, then this is a suitable temperature scale to use. So this is the temperature scale I've used. So actually the most important number here is actually the degrees of freedom. So if you have 50 atoms, each one has 3 degrees of freedom. So it's this number it then uses to work out this scale. So this should work for any molecular system you have. You just need to put in these numbers, or the numbers of degree of freedom, and it should give you a scale that will work. So that should work for any simulation you can possibly think of. So that was running a simulation. So you should have done this by doing your submission. So people, can you just raise your hand if you've managed to submit the Slurm script and then you see the output, the multiple files? Yeah, cool. Yeah, so here I mentioned if you want to run each one in parallel, you would change your command to have 10 number of replicas times the number of MPI tasks to use. And then you would have to change to use 20 tasks in total, which you could do it. You can do if you want to by editing the run script, but I don't think you get a speed up for this small example. Yeah, so now if we go back to the output, so you'll get multiple files. So the most important one is the one that's just called log.lamp. So this is the overall log file, and this tells us which replica is at which temperature at each time it tries to change. So at step 0, we see the replica 0 is at temperature 0 and replica 1 is at temperature 1. That's how we've set it up. And then at time step 100, which is the first time that we've told it to try and do this exchanges, we can see the replica 0 is now at temperature 1, and replica 1 is now at temperature 0. So that's been a successful change, and it's also changed 2 and 3, and it seems to have changed all of them actually, which is, yeah. And then we see again there's more changes, and then we see that some are the same. So we see that these have stayed the same, so it's tried to exchange them, but it hasn't been successful. But that's fine, because you want that probability to be about 30%. So this file just contains a big list of which replica is at which temperature. So that's going to be very important later, because we're going to have to use this information to reorder our trajectories such that we have them at constant temperature. So once again, if we just take one of this time step here, for example, we see that replica 0 is at temperature 8, which is something like 800 Kelvin, and then replica 1 is at temperature 3, and then replica 7 or 8 is at our lowest temperature of 300. So when you're running these simulations, there's additional things that you need to check that you don't need to worry about normally. But one of them is this acceptance ratio I've mentioned. So there's no point running the simulation if they're not able to exchange. So to compute the acceptance ratio, you have to essentially do some maths, where you have to say for each time step, I want to add up the number of successful exchanges, dividing it by the total number of attempts. So that is some maths it's not hard to do, but you're going to have to sort of write a script to do it. So I've provided a script that should do it for you. So if you use this Python script acceptance ratio, I can't remember the exact commands. Yeah, so if you run this acceptance ratio script by this command, you might need to do module load cray Python, because I think the default system Python might not work because it's Python 2 and we want Python 3, but it might work anyway. Let me just see if I have it loaded. It appears I don't, and it still works. Oh no, I do. Yes, so I have cray Python loaded. Yes. So this script prints out the acceptance ratio between our temperatures. So we see that it's about 0.3 and 0.3, which is what our calculator predicted there'd be. So it's always good to check this is the case. We see up here that they change a bit to be higher. So the reason for this is just our very small system size. The calculator wasn't quite correct, I think, but that's not, you don't have to worry about it too much. If these numbers are really, really small, so like 0.01, so 1% chance of accepting, then that's not good. And you want to make your temperature ranges smaller. And then similarly, if it was too high, so sort of more than 50% for these lower temperatures, then you'd want to increase your temperature gaps because you're just wasting time by having this many replicas. So the other bit is you want to make sure that each replica is sort of traversing this temperature space correctly. So you can plot the outputs. I'm not actually going to plot it right now because I don't have X windowing enabled, but I put a picture in here. So you can try this yourself. If you have, if you've logged into Archer with using the -X or the -Y command to turn on the X windowing, then you'll be able to load GNU plot, and you'll be able to plot the file I just showed you, the log file. You can plot each column of it. So here I'm plotting the first column, so it would tell us what is the temperature of the first replica, so replica index 0 at each time step. So we see that throughout our 1 million time steps, we see that it spans the whole temperature space. So this is good. If you're running this sort of simulation, you want to see a graph like this because we see that it's been at the lowest temperature multiple times and it's been at the highest temperature multiple times. So on the right, I have an example of if you see something like this, this means that either you haven't run your simulation for long enough, but we've actually still run it for 1 million time steps. So there's something else wrong. So in this one, I think I just changed the so I changed the swap frequency to 100,000. So it was 100 times. Yeah, it attempted to swap 100 times less. So we see it doesn't traverse the temperature space. So if you see something that looks like this, then you know that you need to go and modify some of your settings. So it might be that your temperature gaps are too small, or it might be that you need to exchange more frequently. So it is quite hard to work out what these exchange frequencies are before you run your simulations. Is not the easiest thing to do. So usually you want it to be about 100 time steps or 1,000 time steps. Good rules of thumb. But if you can check these, you can then sort of go back and do a bit of trial and error and adjust them a bit to make sure you get good traversal. So the trouble is that if you run one of these simulations, it's then quite hard to do any post-processing on it because the trajectory files it writes are there for each replica, but we know that these replicas, they're changing temperature. But to do any meaningful analysis, we are only interested in the temperature, like the 300 Kelvin one. So you need to reorder the temperatures. So that, once again, is not a very easy thing to do. You can't really do it manually because that would take you forever. So I made a Python script to do this. There is also another script on the LAMMPS website that does this as well, but I found it a bit more tricky to use. And I think I made this one several years ago when I was doing this sort of work, my PhD, before they made the one on the LAMMPS website. But I provided a Python script that we can use to reorder. So if you go back to our terminal, so you should see your list of these trajectory files. So if you have these, you can then use this other script, the reorder one. That actually needs some input. So it has a prefix, which is just the prefix is this name here. So we give it that. Then we tell it the number of replicas that there are. So if you run this, you'll see it will, for each time step, it's working out the order and it's writing the reordered files. So now we will have even more files. So where before we just had replica 0 to 9, we now have trajectories for temperatures 0 to 9. So now these are our reordered trajectories. So have people managed to first run using this and get these output files, and then have they managed to reorder them using the Python script? So you can give me a hands up if you've managed to run those commands. Cool. So now you could analyze these trajectories sort of in any way, but as we learned just before from Julien, we can use the LAMMPS rerun commands to do this for us. So I have a folder that's called Rerun. So if you move into Rerun, you'll see there's another script. So here we have a Rerun script, which is similar to the ones we just looked at. So if you open up Rerun, you'll see that once again we have a variable, which is a world variable. So this is the same as our run script. So your rerun scripts are usually very similar to your run script. So you can almost copy a run script because you still have to read in the same data file. You still have to set up the system in the same way. So most of this is the same as the run script, apart from here, because we've reordered the temperatures, we don't need to tell it the temperature. And because we're not actually running any dynamics, we don't have to set the integrator or the thermostat. So we don't actually, I don't have the temperature up here, because this is just rerunning by reading in the coordinates of the previous simulation. So we see it reading the same data file, the potential is the same. But here we're adding in some analysis. So this is a slightly different command, but it's similar to the one we learned before. So this is computing the radius of gyration of the simulations. As this is a single polymer, you can compute the radius of gyration, which is it's essentially a measure of the shape or the size of your polymer. So we're computing that here. So this compute, it will compute one number for each time step, but we want to output an average number. In fact, we want to output a histogram. So this is very similar to the radial distribution function from before. So it's making a fix that computes this average histogram of our radius for gyration. It's going to save it to a text file, which is going to be the histogram. And then these other numbers, I cannot exactly remember what they are, but one is going to be the frequency. So that's 1,000. That's going to be the same frequency as our trajectory files. This tells it how many time steps in total, which is our 1 million again. And I think these commands are the size of our histogram. So it's going to be one histogram from 7 up to 20. So that's just numbers that I know they're going to be that because of the shape of the polymer. I don't think LAMMPS histogram is clever enough to automatically be in a histogram, but it might be. We then have our rerun command. So this is reading in the trajectories that we computed earlier. So you see it's reading from the other directory, and it's reading them each from the specific temperature that we set it to. So it's going to, replica 0 is going to read temperature 0, and replica 9 is going to read temperature 9. Then we just, with the rerun command, you just need to tell it to read in that it's a LAMMPS dump file, and we're just reading in the X, Y, and Z coordinates. So for other things, you probably need the velocities or the forces or other things. But for this radius for gyration, we just need the coordinates. So there's another SERM file, which is almost the same as the one before, but here we're just doing the rerun. And once again, we're using this partition command to run these 10 replicas at the same time in parallel using our 10 MPI tasks. So if you launch this, or this one I think is actually very quick. We'll see. Yeah, so this is now the same as before. When you run LAMMPS using the partition, you get however many things you said out. So you get this overall log file, which actually in this case, I don't think it contains much. No, I just said it's running on 10 partitions of processes. And then it has the 10 separate log files and the 10 separate screens. So if you look at screen 0, this is for our first one. We see that it's printed out. It's what it's doing is it's rerunning. So it's going to be I think this might be the temperature, then the energy. The temperature is 0 just because this is a rerun where it doesn't know what the velocity is. So that's, you can sort of ignore that. And I think this last number is our radius of gyration, which is the analysis we want to compute. Then we also see that it's printed out these histograms that we told it to do. This, you could do this for different LAMMPS computes, but you see it's it's a histogram of, it's filled in. So you can, once again, you can view these quite quickly using GNU plot. So I have provided a plot script, I think, because I do not have expert, or maybe I do. If you use this plot command, actually, yeah, it's plotted, but you can't see it. Well, yeah, it didn't quite work. But if you use this script yourself and you have X windowing, you will see the plot, which I've also put in our file. Yeah, so if you plot the output, you'll see our histograms for each temperature. So temperature 0 is this purple line, and we see that it has a radius of gyration that's sort of centered around 9. Then as you increase the temperature, the radius of gyration gets bigger and bigger. So that's what's expected. So if you were to look at the actual configurations you get, you would see that for 300, it's this condensed globular-like state, and for 1000, this extended state. So this is going back to the picture earlier. If it's in one of these states, it's sort of trapped in the low temperature potential energy surface, and it's quite hard to then sample it. So if we didn't use Replica Exchange, it would stay stuck in one of these specific states for a long time. But as we're using Replica Exchange, you can access these extended configurations, and then as it moves back down the temperature, it will get into one of these states, but a different state like this. So for this toy system, it's a bit contrived, but you can imagine for a more complex polymer system, you can then sample multiple of these compacted states by using Replica Exchange to access these larger states. So just more information. LAMMPS has its own page that essentially tells you what I've been telling you, and for other multi-replica bits, but this is just one of the slightly more complex things to do without sort of concrete examples of the whole process, but there's more information here. So that's all for the bit. I didn't put any actual exercises in because I didn't get around to it, but things, if you want to try different things with this, it will be worth doing it again, but with a different temperature scale. So you could try just using more temperatures or even less temperatures. So you could do it using just 4 temperatures, or you could go and use the temperature calculator, and you could set the higher temperature to a much bigger number. So you could go up to, like, say 2000, see how many temperatures you need, and you could run it again, and everything we've done should work. So if you want to try that, that is worth doing. Otherwise, any more questions, let us know, or any questions about any of the rerun stuff we covered in the session before, you can ask them now. So could you explain a bit more about the replication on parallel nodes? So is this asking how you would do it using each task in parallel, or if you wanted to use, if you had a larger simulation, you wanted to span across more nodes? So it works in the same ways. If I go to my input script, actually, yes, if you wanted to run it with each replica in parallel, you would just need to make sure your numbers essentially add up correctly. So if I put this to 20, I change this to 2, it's now going to run 10 replicas, each using 2 cores. So if we run this, so it's actually a good point in general that I haven't covered here, because as this is a small system, you want each thing in serial. But in general, if you have a large system, you're going to want to run in parallel. And you have to be quite careful how many replicas you choose, because you want it to fit with your computer. So for Archer 2, you want a number which is a factor of 128, because that's how many cores there are on a node. So you might want so let's say you could choose 64 replicas, and then you could run them each on 2 cores, but you could run them each on 8 cores, and you'd use 4 nodes. So it's quite a specific thing when you're doing these. You're dictated by the hardware you have, because if you start using sort of strange numbers, you end up wasting compute time, or things don't run as well if they're not shared properly. So it's similar as what Julien was saying about how when you're using the hybrid OpenMP, you want to have a look at the hardware. So on Archer 2, you have these there are these each processor. Each node is sort of 2 processors, and each processor has these sort of 4 distinct regions. So ideally, you want to split things up to fit into this specific hardware. So for Replica Exchange, you want to do the same thing. So ideally, you want to divide it up into these chunks that fit well into your specific machine. So for Archer 2, that means you want numbers that are factors of 128. Otherwise, you end up with odd combinations. So our simulation should have run with 2 nodes, so 2 cores. So we can see now that it's run. This is 1 replica, and it's run it using 2 MPI tasks. So actually, that's worked. It's not any faster, I think, than before. So before it was about the same time, but that is because this is such a small system. It's only 50 atoms. I think in general, to make use of parallelization, you want, I think, definitely more than 100 and probably more than 1,000 atoms per core. So this is just a small example where you're not going to see a performance boost. But this would also work for more. This will probably crash if I try this. But if you wanted to do it with more nodes, you could set this to 2 nodes. It's not going to work anymore, actually. Yeah, so larger simulations, you want them distributed. You essentially do it in the same way. So here you would go 2 nodes with 128 cores per node, 1 CPU per task. So if it was a single LAMMPS simulation, this would now run with 256 MPI tasks across 2 nodes. For a Replica Exchange one, you then have to make sure you specify this partition in the correct way. So if I was doing this, I would maybe then go, let's use 32 replicas, and then I need to do quite a bit of maths like I can't do in my head. So you would go 32 replicas with 8 cores. So if you're using a larger system, you are going to need more replicas to span the temperature space. So you might end up with something like this. Like if you knew you needed about 32 replicas, you could then go, all right, I can either use one node and run them on 4 cores each, or I can use 2 nodes and I can run them with 8. So you always want this number. So 32 times 8, you want that to equal your number of nodes times the task per node. So you get an even bigger system, you would do something like 128 times 8, then you would have to use 8 nodes. And this would split it up equally. If you end up doing other things, so if you're using 8 nodes and you were using, let's say, 100 replicas, you could do this and it would work, but you're wasting a bit of time. So it's probably worth you actually using 128 replicas, or even you might try and reduce it to 64 and see if you can get away with it. But yeah, you always want this times this to equal the nodes times the task per node to make the best use. And for a different system, that would be different. Yeah, other systems have different numbers, so you are dictated very much by your hardware.